So if you recall, we have been trying to do some sort of covering and packing, and as the board suggests, last time we proved that for in a tournament either you have k arc disjoint cycles, directed cycles, or you have some order k arcs which if you delete them there are no directed cycles. So if you look at the proof little bit, actually we proved something very stronger. We proved that in tournaments either you have k directed triangles or you have some order k arcs which destroys all the cycles, right? Because how did we went about the proof? In the forward direction, all we cared about, we picked up, look at the proof, no? What did proof do? It just picked up k triangles, right? So basically what we proved is actually that in tournaments either there are k arc disjoint triangles or you have roughly 6k arcs which if you remove then there are no directed cycles. Okay, so it was a bit more than this. Okay, so today we will move to a different topic, but before we move to different topic, let me tell you a little bit more about the things which we did. So as I told you, even in general digraph you can prove such a theorem, but it is very difficult. There are people have asked what are the other structures for which we can prove such Edge-disjoint. They are also known as like subset versions, where you are given a subset, and for example look at a cycle and subset version is that you are given a fixed subset S. You have to say either there exist k vertex disjoint cycles that must intersect these vertices, or there exists some order k vertices which destroys all cycles that pass through S. So it is bit more general than this, because when you put S equal to whole vertex set of G, we will get back this theorem. So people have also proved many of such variations, and you look Edge-disjoint, JCTV people, and you will find like lots of papers results coming in. People have also put some groups on the arcs and edges and things of this nature. Okay, but a very simple graph class for which it doesn't work, you can't prove the following theorem, that given a graph G and integer k, does there exist k vertex disjoint odd cycles, or there exists an odd cycle transversal of f of k size? Such theorem doesn't hold. You can come up with a family of graphs where like number of vertex disjoint cycles are like roughly constants, but the number of vertices or edges you need to destroy all odd cycles are still function of n. Okay? Okay. Okay, so let me motivate the next study with slightly different question, and then we will go to the whatever we want to do. So let me ask you following question. Okay, So you are given a graph G, okay. It's a mix of, this question is largely motivated from lots of applications or whatever you can call it. And what I want is that I want you to give me H subgraph of G with the following property. What is the property you want? That I want to say that H is one edge fault tolerant, okay, with respect to some measure. What is the measure? I will tell you that I want to say that for all E, what is the property I would like to maintain, that G minus E is connected if and only if H minus E is connected, okay. So I want H, which is a subgraph of G, and what I want H should have as few edges as possible. H should have as few edges as possible, right? That's my goal, okay. So I want a subgraph of G which has a very nice property that it is one fault tolerant with respect to connectivity, right. So if you wanted to know whether a graph G is connected after deletion of some edge, you can just check the same thing in H and be good with it, okay. So this is like what is called one fault tolerant connectivity subgraph, okay. So imagine G has two, okay, so what do you think could, what could you do?
Union of cycles.
Okay. What do you mean by union of cycles?
As in you pick all the edges which lie on some cycle in the graph G.
Okay.
And you put those edges in the graph H.
Suppose look at complete bipartite, complete graph on n vertices, right? Okay. Click. Every edge belongs to some cycle.
Yes.
So we will end up picking all the edges, no?
Yes, sir.
Yeah. So I want to find H, which is a subgraph of G, which has the following property. For all E, G minus E is connected if and only if H minus E is connected. If I forgot this, I said find H, which is a subgraph of G with the following property. G is connected if and only if H is connected. What is your witness? If I did not say this, I say, hey, can you find H subgraph of G with the following property? G is connected if and only if H is connected. Then what H can you think of? Yeah, but G could be as bad as click, and I want H should have, look, G itself works in any case, even G works here itself, right? You take H as G itself, of course, like now G minus A E is connected if and only if H, which is G minus E, is connected. So G is always a good, like G is always a good solution to H. But really, if I asked you to give me a connectivity certificate for G, all you can give me is G. If all I care about from you is that if two things are connected in G, they are connected in my H.
Take a complete graph and
Take a complete graph.
as a G, and subgraph as a subgraph, take the biggest.
G is not something which you decide to get. G is something which I give you. H, given G, all you can do is get me H from G.
So you need procedure.
procedure or an object? Think, right, why it will not work. Given a graph G, if I keep a spanning tree H, suppose G was connected, what will be H? H is like spanning tree. Why? If two things are connected in G, are they not connected in H? They are. So H is a good certificate for connectivity for G. And how many edges it has? N minus 1. And if G was connected, can I have a certificate which is less than n minus 1? Think about it, right? So it is clear that if G is connected, if and only if H is connected, then an object which I can take H as is spanning forest of G, right? Now I want you to have an imagination, forget it, H is a spanning forest of G and this, okay. So what did you do for connectivity? You kept one spanning tree, right? If my graph had two edge disjoint spanning tree, suppose okay, G has two edge disjoint spanning tree, T1 and T2. What is this? Suppose disjoint spanning tree, and I take H T1, this T1 union T2 as set of edges, will this work? You delete an edge, okay. First of all, if you have two edge disjoint spanning tree, if you had, I mean that's a bad way of looking at, anyway this graph is connected even after deleting one edge. But just to keep in head, what is happening, if I delete one edge, I can only make disconnect this one, right? But the other T1 which does not contain this edge, right? So what should I bother about? So the only thing which I should, like if the graph does not have two edge disjoint spanning tree, which in some sense means there are some bridge edge, like if I delete this one edge, the graph, but if I have a spanning tree, should it contain all the bridge edge? Every spanning tree must contain all the bridge. What do you mean by may not? How can it be connected then? Think about it. Any spanning tree must contain all the bridges of my graph, because it's a spanning tree which must connect left from the right, and there is only one edge to go from left to right. So my spanning tree must pick up this edge, it has absolutely no choice, okay. So maybe if we take this pattern and take the first thing is that let's take T1 as spanning forest of G, okay, and then I take T2 as spanning forest of G minus T1, right, and let's take H as T1 union T2. Does it work? That's a question for you, okay. I'm not going to do it, okay. So what I want to do that, so this is why spanning trees are very, very nice object, because if you have several edge disjoint spanning tree, then in fact by just this simple computation allows you to store path between every pair of vertices, several paths which are vertex disjoint, edge disjoint paths, right. Every tree between those two vertices you have a path, right, which is disjoint, edge disjoint from the path between those two vertices in the other one, right. So what happens here? Look at your tree and look at your tree here, like, or forest or whatever you have got. This is my T1 from here and T2 from here. If you had two pairs of vertices which had two edge disjoint spanning tree, two edge disjoint path, what happens between them? I claim to you they are connected here. If you had two vertices U and V in my graph which has two edge disjoint spanning tree, okay, two edge disjoint paths, no, my bad. Okay, I claim to you, then u and v will be connected here as well as connected here. So you are preserving two paths between them, which are edge disjoint. If two vertices had k edge disjoint paths, and if you took up, you did the same process T1, then deleted T2, then deleted T3, and so on, you will preserve them. Look, I am making a statement without proof. Okay, this requires proof. Okay, but it is possible to solve. So these edge disjoint spanning trees, or spanning tree, or edge disjoint spanning forest construction, because we don't know whether it is spanning tree or not, but we did edge disjoint. So like this way of keeping a spanning forest is a very interesting question, and this comes from this fault tolerant network and this and that, right? You do not want to have enough, like too much wires, but you still want that if some edge faults, there is a way to reach. So this is why spanning trees are very useful objects, even in graph theory as well as in algorithm and this and that. So that led people to question, okay, fine, what should be a sufficient and what is a necessary condition that my given graph G will contain k edge disjoint spanning tree? Like, so right now this was largely an algorithm way of thinking about this, but now go back as a graph theorist, what will I start thinking? Okay, fine. So if I tell you, what is a, like for example, if I ask you the following question, what is the property that given graph G, it contains one spanning tree? Connected? Okay. But if I ask you, what is the property of graph such that if I give you two graphs, like if I give you graph G, what kind of property that you think or condition that you can put on this tree so that you can say, hey, if this graph satisfies this condition, then it definitely has two edge disjoint spanning tree. Okay, you get the at least. Okay, so what is the question we are asking? Okay, so the question we are asking, so please keep this in mind, it's one of the most beautiful set of things which people are doing algorithm by, and this is a very strong because look, algorithm is nothing, right? But these questions are even meaningful for graph theory, is that what is the smallest h that we could come up with, right? And I define this with respect to connectivity. People can define with respect to, okay, so here is a question which at least I have been troubled for a long time, I'm still troubled, I don't know the answer, so let me at least pose this question. Okay, it's an open question, so if you solve it, you can get a very good paper out of it. And I don't think it's very hard, okay? So what I want, okay? Okay, so I want G, H should have as few edges as possible, okay? But my properties which I expect from this is this, okay? Such that for all E, maximum matching of G minus E is equal to maximum matching of H minus E. Right? So I want a one fault tolerant subgraph with respect to maximum matching. Okay? When G is bipartite, I can come up with an upper bound with size 2n, like as 2n edges. But when G is not bipartite, I don't know any bound. Okay? And this is not a algorithm question, this is just a graph theory question. Right? That what is my question? Given an arbitrary graph G, I want to come up with a subgraph of this with the following property. If you delete an edge in G and look at the corresponding edge, look what could happen, that edge even may not be even there in H. So H minus E is H itself. So for those cases, what you want? Maximum matching of G minus E is equal to maximum matching of H, right? So if you notice, these are very, very simple things to do, okay? So one trivial thing is that how do you people start about it is that, okay, let me start with H equal to maximum matching of G. So that is what you will start with. Now notice, if you delete any other edge which is not on this maximum matching, because this maximum matching is there, maximum matching of, so the only problem is when you delete from this edge and there exists some maximum matching that avoids this edge. then in your H there should be a witness that, hey, still the maximum matching of H is same as maximum matching. So you only need to care about these edges. So what people generally try is that, okay, I find this, is there some augmenting path? Okay, I add it, but augmenting path could be very big, right? So if you, for every edge, if I add an augmenting path, it's like already you have added like n square edge, possibly in the worst case. But so can you come up with a structure of augmenting paths which minimizes number of edges? So if someone can come up with, to me at this point of time, any interesting bound n to the power 2 minus epsilon, it will be very interesting. Like, you get my questions, what I want? So look, like just this takes care of every edge in my graph except this edge itself, right? And for this edge you need to do something special, okay? I don't think it's extremely difficult question or something, it's just that, okay, I don't know how to do it, okay? So you can ask all kind of questions. You can ask for cuts, you can ask for flows, okay? Anyway, so our topic of today's and next day's discussion is around these spanning subgraphs like trees and the conditions of existence of many such trees, edge disjoint many trees, okay? Okay. So that was the motivation part. Now comes, so what I want, given a graph G, okay, and an integer k, okay, I want conditions such that it implies that G has k edge disjoint spanning trees. Okay, so I want, can you think of a trivial condition or something that you say, okay, if this will happen, my graph definitely will have k edge disjoint spanning tree. What's a natural thing to think in these terms when you start to think of such necessary condition or such obvious condition? Which is same as, which is, yeah, so if you say this, what does that imply? Graph is k edge connected, okay, so what he is saying that one obvious condition is, but like I would like her to prove this, right? Okay, so that what she said is that, so what she said, okay, so one seems like an obvious condition for every pair of vertices u comma v in v cross v, there are k edge disjoint paths between them, which is same as saying as G is k edge connected, meaning G is k edge connected. You at least need to delete k plus 1 edges if you want to disconnect G, okay? So this is what this condition is equivalent to this condition. This is exactly what, okay, if you say graph G is edge connected, is it obvious? That if the graph is highly connected, edge connected, I mean, why k? I mean, let's say okay, can be like, can then I say something like, if I give you not only k is connected, such highly edge connected, can I still say, can I then say at least that there are T1 to Tk edge disjoint, because k and k are like too close, but I said forget k, I gave you graph which is even much more highly edge connected than you can think of, at least then can I say something? Even for say 2 edge disjoint spanning tree, forget about, just let's say k equal to 2, okay, can you come up with any connectivity constraints except n minus 1. Don't tell me n minus 1, then that's like a click. Okay. But something which is a function of k. Okay, so let's ask ourselves why highly edge connected is not, like, why it is not able to tell us something, because we know only an obvious algorithm at this point of time. Okay, we like if we only know an obvious algorithm, suppose graph is hugely edge connected. Okay, say for example some f of k connected. Okay, okay, why it is not obvious that, I mean, that this implies something. Okay, so what happens, I take the first spanning tree, we are only in the looking for the case k equal to 2. Okay, I took first spanning tree, deleted, right, deleted. Now what can happen? Unfortunate part is that this graph could get disconnected, because if this is connected, then we are happy. Then we are happy, because then I will find another spanning tree and we are done. Because what I did, I find any spanning tree and then I am looking at G minus T. If G minus T is connected, then I am very, very happy because I found two edge spanning. Yes? Edges, just edges. Like what I mean is that when I say G minus T is like vertex set remains the same, edges are like E minus edges appearing on T. This is what I mean when I say G minus T. Absolutely no vertex, only edge removal. Okay. Now, okay, so what happens if I look at this, graph becomes disconnected. So if I can find a spanning tree such that it maintains the graph to be connected, then we will be happy. Okay. Okay. So if I could find it, but the graph was so connected, no, so connected, so hugely connected. What happened then? Like, I deleted this T and suddenly I got disconnected pieces. I got suddenly disconnected pieces. Okay. But look at my original graph. Look at my original graph. I have this. Look at this. Any two part. How many edges are going across if the graph is highly connected? At least that many, right? Because otherwise I couldn't. So any part must be having, partition must be having at least these many edges. Do you agree? Okay. So suppose if I graph had two spanning tree, edge disjoint spanning tree, two edge disjoint spanning tree, and now look at this partition. Suppose graph had two edge disjoint spanning tree, then this partition will still be, look at this particular partition. What can you say here? You get my point? Okay, or rather let's look at this. This partition tells us something very interesting. Okay, so I'm just trying to get to this partition and say, okay, fine, let me fix some partition of my vertex set. Okay, some partition of my vertex set, P1, P2, PL in L parts. L parts, partition of my vertex set. And now look at any T1 and T2. What are these edge disjoint spanning tree, edge disjoint spanning tree. Now I'm asking you, how many edges of T1 are like this, like across? Okay, so I'm asking how many edges of T1 are crossing. Okay, and what is a crossing edges? An edge with one endpoint in one partition part and the other endpoint in other part. Those are crossing edges. Okay, so these are cross edges. Okay, and if you have an edge here, not crossing edges. Okay, so this is what it means by. So I'm just asking you, I give you a spanning tree T1 and I'm asking you, I gave you L partition, how many edges will be there? Okay. So let me make your life easy. Suppose every partition is singleton, so L is like n. Now please tell me how many edges are crossing? No, no, no. Please, what are you saying? What are, you are saying?
So you are saying now that
Every vertex is a partition. Like look at a partition where L is equal to n, which means every part consists of single vertex. And now I'm asking you, from my spanning tree T1, how many edges are there? No, how many cross edges are there over sum? I'm not talking about single. Exactly equal to? Okay. So now go back and tell me how many edges are there if I have L parts where L is strictly less than n. Because if L equal to n, all of you agree that if T1 is a spanning tree, then all the edges now becomes crossing. So it is exactly equal to n minus 1. But what happens if L is strictly less than? What can you guarantee? Say for example L equal to 2. What can you guarantee? L equal to 2. What can you guarantee? At least one edge must be. Maybe more than one edge. But if I have a spanning tree, there will be one edge definitely. And there could be possibility that there is exactly one edge, because maybe if my these two partitions are like, say this edge is a bridge edge, and if I put this two, okay. Okay. So L equal to 2, all of you agree at least one edge. Okay. Suppose L equal to 3. It is just for you to find the right number. Okay. So now we have just 3 partitions. Okay. 1, 2, and 3. And I'm asking, how many edges from T1 must be a crossing edges? Can you give me some guarantee? For 2 you gave me guarantee of 1. For n, I know it's n minus 1, but now I have drawn 3 parts. Please tell me how many edges must be going. Why? Why at least 2? So you are saying at least 2 edges of T1 are crossing. Why? Huh? Meaning I still don't get you, Sonak. What?
Suppose there are less than 2 edges, then we can show that T1 is not connected.
Okay. So what is not connected?
The spanning tree.
Or T was not connected, because if there is only one edge, then it must be going across to some part, and then who will connect to him? So first thing we observe, very nice, that look at any partition of my vertex set, spanning tree must cross. This is what n equal to 2 meld, right? Okay. Now you say that okay, fine, I make your life much nicer. I added 4. And let me write down a number. N part, how many edges we had? Okay. 2 part, how many edges we had? Guarantee, I'm only talking about guarantee. 1. When we had 3 part, 2. We have 4 part, how much? And then you should be able to please tell me the pattern. It is no pattern. Is there no pattern here?
if we have L part, then at least there are at least L minus 1.
Okay. So here is a conjecture. Okay. So what she says, if we have L paths, then at least L edges of T are crossing. Sorry, L minus 1 edges of T are crossing. It is consistent with whatever we did. How do we prove this? Huh? Induction on what? whatever you want to use, please use. Give me a proof. Yes.
Can you convert this pattern into a recurrence and can we
By what do you mean by this? This is a loaded statement. Okay, so let's unload it. What do you want to write?
or we can give it as a sum of previous like 3 like 2.
How will you give a sum?
T4 is equal to 3 plus T2.
So look, if you are able to write recurrence, you better be able to come up with an induction proof. You understand that point or you don't? Yes, no. Okay, you understand that recurrence is exactly equal to induction, right? So if it is equal, then give me an induction proof. And if you are not able to come with an induction proof, then there is something that you need to modify or change to make your recurrence work. Like, keep that as a fixed thing. Dynamic programming is induction, because dynamic programming is recurrence. Recurrence is induction. Dynamic programming is not memory. Always remember that. Okay. So similarly here, so algorithms, when it wants to apply induction, it takes recursions, reduction, everything itself. What is reduction? Self-reduction is what? It's induction, right? So algorithm takes induction as reduction, recursion, whatever. And graph theory or maths, it just says, okay, let me be with my induction. Okay. So what will be an inductive proof if you have to? Let me tell you, it's obvious. It's extremely obvious. It is as obvious as a spanning tree has n-1 edges. Huh? Guys, make a vertex for every part. Okay? Make a vertex for every part. If there is an edge between two parts, please put an edge between them. Okay? Right? That's all that I did. What is the property? If there are less than L-1 edges, what can you say in this graph? It is not connected. If it is not connected, you look at those parts and look at those parts. You just now told me that every spanning tree must cross this. What happened to that? Right? So that's it. So once look at the partition graph where every vertex is a part, and if two parts has an edge between them, you just put an edge between them. That's it. That's all. Now I am saying, if this graph contains if this graph is, or say this way, either this graph is connected or this graph is not connected. If this graph is connected, then how many crossing edges we have? At least L-1. If this graph is not connected, then look at the connected components. Pick up one connected component in one side and rest every vertex in the other side. In this part, you have no edges going across, but you just now said that every spanning tree must cross this. Okay, done. Okay, so if I had two edge-disjoint spanning trees, then what can I say? Huh? What can I say? Huh? Do this the same math for every year. There is edge-disjoint spanning tree, no? And if I have k, k times. Okay. So this looks like a necessary condition, no? It's sufficient also. Okay. So what's our theorem? Our theorem is, so I'm just going to write down the theorems. Okay. So what will be theorem? So the theorem is, let G be a graph, okay, and we are going to talk about multigraph. Okay, so what is a multigraph means? I allow everything you can think of, self loops, parallel edges, everything. Okay, because this makes the proof cleaner and easier. But if someone tells you what is a degree of a vertex with a self loop, it's always 2. Okay. Now why do people say self loop as 2? Because look at cycle, no? What is a vertex? What is the degree of this vertex? So if you do short circuit kind of thing, what will you get, right? And short circuiting should always preserve degree. So that is why we call it's a let's say notation or whatever. It's a notation which makes everything consistent with whatever you do for simple graph. Anyway, okay. So let G be a multigraph. Okay. Then G has K edge disjoint spanning tree if and only if for all partition P, P1, P2 of PL of Vg, for all partition this should happen of Vg, there are at least K into L minus 1 crossing edges. Okay. Is the statement clear at least? Right? And I have proved one part at least. What I have proved? If you have a K edge-disjoint spanning tree, then this happens, right? Because that is how we came up with. So the difficult part is how to show this. Okay. So this is something which I have not shown. Okay. So I will just build up to the crescendo that they call, no. So now I want to go back to what she was saying. Now can you tell me that if graph is this much edge connected, it must contain some edge disjoint spanning tree using this theorem. I want to prove the following. Wait 1 second. So what? So she has a question. So let me write it down and then you can answer. So I want to prove or a statement. This is what I want to say. Okay, if G is X edge connected, then G has K edge disjoint spanning tree. Okay, what is the value of X? My question is, what is the right value of X? What is the value of X? This is what I want to prove, right? So I want to say, look, in fact, if graph is sufficiently edge connected, then you do have K edge disjoint spanning tree. Okay, how do we prove this? If I gave you a theorem and you want to test whether a graph has a K edge disjoint spanning tree or not, what should you do? What should you demand? Like, what should the condition be satisfied? So for every part, number of edges going across should be at least K times, right? So you should think of what is the condition on edge connectivity should I come up with that this condition is met or this condition is satisfied. So what should be that edge connectivity? Look, I broke up questions. Okay. K edge connectivity. Okay. Why do you say that, silly? Yeah, let's try proving. We'll see. We'll fail. We'll fail. They have not convinced her though. Okay. I go here. I have to start with some L partition. Okay. And how many edges do I need to show here? At least 2 times no, sorry, k times L minus 1. And you are assuming the graph is k is connected. Let's see. How will you go about proving this?
Find the parameter in the graph. Like we know that there are this many.
We don't know, that's what we are proving. Absolutely, we don't know that. What we want to show, my graph contains k edge disjoint spanning tree. That's what I want to prove, if graph G. And to prove that, I am trying to use the sufficiency condition here. Because if I prove this and if this theorem is correct, as a corollary I will get that this statement is true. Okay. So to do that, I said let's start with L part, and I want to say something about it. I want to count the number of crossing edges. Let's fix P1 and tell me how many crossing edges are emanating out of it. At least. How many edges are emanating out of P1? How many? At least k. Okay, fine. So k, and there was nothing special about P1, no? How many edges are emanating out of P2? K. How many times? L times. Are we done then? We should be very happy, no? Because we are getting some L times k, no? Really? We are counting the same edge twice. So actually, so number of edges that are going across is, so if my graph is lambda edge connected, right? What can I say? Number of crossing edges is greater than equal to L times lambda divided by 2, right? Because each edge can be counted. So look at, if this is an edge from here, so this crossing edge will be counted for P1 as well as for some other partition Pi. So number of crossing edges is at least L times lambda by 2, and this should be greater than equal to, what should be this greater than equal to? L times, no, this is what I want. Okay, my bad. This is what I want. So can I get, right? So this is like, lambda is like, at least lambda should be 2k L minus 1 divided by L, right? Is that okay? Lambda should at least be this much, right? Because crossing edges, if my started with lambda edge connected graph, then at least we have L times lambda by 2 edges. And if I want to meet this condition, this number of edges should be at least greater than equal to k times L minus 1. Because I want to get what is a lower bound on lambda, right? So if I take lambda is, so that implies that lambda is at least 2 times 2k into L minus 1 by L, right? So that implies if I take lambda greater than equal to 2k, we should be fine, because L minus 1 by L is close to 1, right? So what did we prove here? As a corollary, that if G is 2k edge connected, then G has k edge disjoint spanning trees. Okay, is that fine with everybody? So this is packing version of our theorem. Okay, so this is what, this is called packing version of our theorem. Look, even if finally if I tell you the proof of this you don't understand, I can live with it, but I at least want you to know the statements of this thing. They are very useful. You get my point? Like, I will tell you a proof because that's a graph theory course, but what I expect for you to take back is statements and the statement which will prove these statements. That is, the statement which proves this statement is amazing, and the proof which I knew was like from those 60s and 70s, because that is what I have taught. But in 2015-16, people came up with generalization of this to matroids, and for that they came up with a very beautiful theorem. So if you take that proof and you say instantiate to graphs, you will get the proof, and that statement is very beautiful. Proof is extremely simple, elegant, but like we will do, I mean, why someone will think, I don't know. Okay, so this is a covering version of them, and we will derive both of these theorems from our general statement. Okay, so what is this called? This is, let's call this packing theorem. Okay. Now I am going towards covering theorem. What is a covering theorem? So covering theorem, what will be dual of this covering theorem? What is the minimum number of spanning trees that can cover all the edges? And what is the meaning of that? So I will say that these spanning trees cover all the edges if, look, these spanning tree need not be edge disjoint, first of all. Okay, every edge occurs at least in one of the spanning trees. Okay, so so this is packing theorem. So what is the covering version of this theorem? Covering version. So I'm going to say a set of subgraph. So you are given a graph G, a set of subgraphs H1, H2, HL covers edges of G if what happens? For all E in E of G, there exists I such that E belongs to edge of Hi. Okay, so that means that every edge is covered by something. Okay, so in packing, what is our goal? We'll to pack as much as we can. In covering, will be to cover it with as few subgraphs as possible. So in that sense, they are dual to each other. Okay, now so now people study this with all kinds of Hi. Okay, but we will study this with Hi being spanning tree. Okay, so invariably I am assuming the graph is connected, otherwise it may not even have a spanning tree. Okay, another thing, this H1 to HL may not be edge disjoint. Okay, so now I want to say the same thing. Let G be a multigraph. Okay, I want to say edges of G can be covered by at most k spanning trees. I want to. Can you come up with a condition on G? You understand my point? I say, look at a graph G. If it satisfies these set of conditions, then actually you can find some k spanning trees such that every edge occurs in one of those spanning trees. Right? So here we said, right, if something, so can you come up with a analog partition statement for covering version of this theorem? You get my point? Right? I want to say, look, if you want to cover your edges of your graph with some k edge disjoint spanning tree, then it better be that some condition on partitions of this vertex set be satisfied. So I only want you to ask, what do you think should be a necessary condition? And then we will worry about sufficient condition. But what should be the necessary condition? Like one necessary condition that you came up for packing version is that for every partition, at least that many crossing edges is going across. Huh? At most. Okay. That's for the yeah, that's for okay. Okay, or What else can you think? Okay, so for example, okay, I like partitioning is not a right thing to say. Okay, I shouldn't say partitioning because that's like misleading. Okay, some condition. Okay, forget about this. Okay, so let's try to do for k equal to 1. Okay, k equal to 1. I want to cover my whole graph with one spanning tree. So graph should be spanning tree, no? Very nice. Okay. So how many edges do you think? Let's fix some u subset of Vg, and I ask myself how many edges a graph has here. My graph can be covered with a tree. My graph can be covered with a tree, and now I ask you a very simple question. I give you a vertex set of my graph, and I ask you how many edges graph induced on U has. What? 0? Why? Oh, but I'm not asking a lower bound, I'm asking an upper bound. Look, so for example, if u equal to v of g, okay, how many edges should this graph have? It can be all the edges of this graph can be covered with one tree, right? So every edge occurs on this tree, no? And a tree can contain how many edges? At most n minus 1 edge. So for u equal to vg, how many edges this question has upper bound of n minus 1? But I want to generalize this, and I want to say, look at u, any vertex set of any u which is a vertex set of G, and I'm asking this question to you. How many edges graph induced on U can have? If you hope, huh? I know. Okay, I'm only telling you my graph can be covered with one spanning tree, right? K equal to 1 means I can give you a spanning tree so that every edge occurs on this spanning tree. Given this statement, if I give you a U subset of Vg and I'm asking you, graph, how many edges graph induced on U can have? Okay, so so a generalized statement is graph induced on U should have at most U minus 1 edges. Why? Because you look at a graph induced on U, look at all the edges of U that occur on that tree. That also forms here what? What is that? If I forget all other vertices, okay, or you look at this tree T, look at the tree induced on U. Does it contain all the edges of my? Because that's the only place it has, right? And tree induced on U will be tree itself, and it contains all the edges on U. So this is fine. Okay, excellent. So now if I have k equal to 2 or k equal to 2, then what should I have? I want to ask the same question, but now I'm telling you, look, I don't know whether I can cover with one spanning tree, but I can cover all the edges with 2 spanning trees. And now if I give you U subset of Vj, okay, and I ask you, how many edges does G has, first of all? This should be simple, no? If I told you that I can cover all the edges of my graph with 2 spanning trees, how many edges my graph can have? At most 2 times n minus 1, no? Because look at T1, look at T2, look at your any edge. Either it occurs here or it occurs here. How many edges this has? At most n minus 1. How many edges this has? At most n minus 1. So how many edges in total a graph can have? At most 2 times n minus 1. Okay, but what about graph induced on U? how many edges this is upper bounded by? Yes, Pratik, you look a bit confused. Okay, so how many edges this can have? Why?
This T1 induced on like these u many vertices covered.
Okay. Okay. So basically, idea is very simple. Look at u, and look at your u, and you just basically you look at T1 u and T2 u. If I have an edge with both endpoint in u, where should they belong to? Either on this tree or on this tree. Is that okay or not okay? Pratik, is that okay? Now you look very confused, so please tell me. Yeah, it could belong to both. That's perfectly fine. I mean, it definitely belongs to one of them, but because our trees are not edge-disjoint, of course it is possible that this guy, for example, I'll give you an example. Look, I think we can cover this tree with two edge-disjoint spanning tree. Right? How? You take this as one spanning tree, right? These blue edges, right? Now you take this as one and this. So what you are getting? You are getting this as one spanning tree. Then I got a spanning forest containing this black. Like I said, delete this red, take. But now if you just complete it to a spanning tree containing these two edges, right, it will contain some of the red edges, right? So of course an edge will occur. That absolutely. But all I am telling you that even if I, so now what happens? So if I look at this, and now I will have to add some, say, red edges. Okay, so this spanning tree is going to be like this, like this, like this, like this, potential, right? Now look at every edge. It is either on blue spanning tree or on the red. But the red spanning tree, blue spanning tree, red spanning tree has huge intersection, right? Except these two, like 1, 2, 3, 1, 2, 3, they have intersection. So they will have. But all I care about, look at your edges. It belongs here. So forget about those edges. Now look at all the edges which this guy not covered. It must be on this, right? But even if all of these edges are new here, still we are not incurring more than n-1, and that's it, right? So it is, yes, so it is as simple as this, okay? What does it imply? So if I had k trees, I will just have, for this question, my answer is very simple. Okay, fine. If this is your edge, consider T1u, T2u, Tku. How many edges this guy has? This guy has at most mod u minus 1 edges. How many edges this guy has? Right? So an obvious bound is this, right? And now definitely this is true. And look, you can't prove better than that, because graph, imagine a graph which is just a, you look at, like it's a exactly union of two edge-disjoint spanning trees. So you can't do anything better than this, right? Okay. So what is our necessary and sufficient condition? So this seems like that it is a necessary condition, but what is amazing that this is a sufficient condition. Okay. So let me write down. This is packing theorem, and now let me write down the covering theorem. Okay. And then, okay, then I will give you some comments, and then I will tell you the theorem which proves both of them. We will not prove the theorem, but we will prove that if we prove that amazing theorem, why we can prove both of them. Okay. Okay. So our covering theorem is let G be a multigraph, okay, then edge of G can be covered with at most k spanning trees if and only if for all u subset of vertex set of G that's it. Okay. So the right way of looking at some of these things is, okay, so I let me make some noise about this, and then that kind of tells you how these things are like in head, what is happening. Okay. Should I just remind you of anything? Look, imagine yourself that why you might ask, why you are not just saying that graph has at most k times n minus 1 edges or kn edges. It should be covered with small number of spanning trees. Why we are not making such statement? Why we are doing this? Every subgraph has this and that. Why not just number of edges is enough? Number of small edges is enough to prove this theorem. Why not that? You understand my question? Say even simple graph. Why we are going over every subset and trying to put some condition on every subset? Why not just some global constraint that number of edges in my graph is small? Why is that not enough to prove this statement? Okay. So for example, look at this, right? Imagine that I have a root n size clique in my graph, root n size clique, right? Root n size clique, and n minus root n vertices with just like 1 edges. How many edges this graph has? Like some order n edges, no? Like some 2n. I don't think more than 2n edges are there. Right? Right? Like less than 2n edges. Like you can say root n by 2, right? Or you can have say root n by 4. I'm sure now root n by 2 choose 2 is less than n. Okay? And this is like 4. Okay? So this will give you this many edges. This so less than 2n. That's all that I'm trying to tell you. Can you cover this with? Look at our upper bound proof. Now we said suppose we could cover with 2 edge-disjoint spanning trees. Then actually we are saying something more. Then in fact what we are saying is that if we can cover all the edges of my spanning tree with 2 trees, then we can also cover the edges of this object with 2 spanning trees. Not possible, no? So if there is something dense hidden, you can't have your argument. So if I want to avoid some dense hidden denseness in my graph to be removed from the statement, I need to come up with a statement which talks about everywhere. So it's like I can cover you with small number of edges if your graph is almost sparse everywhere. You get my point? Like, and how am I saying that almost sparse everywhere? By coming up with this condition, right? What is almost sparse? Oh, you look at any induced subgraph, you have not too many edges. You know what this concept is called? What is this object? This object has name. A graph G which can be covered with k spanning trees are called. Have you heard the word arboricity? Have you heard this word called arboricity? Degeneracy? No? So in distributed computing this word is like all over the place, called arboricity. Okay? They are amazing graph classes. Okay? Amazing graph classes. Okay, and they are very vast. Okay, they are very big graph classes. This is called arboricity. Okay, okay. So this is precisely the definition. G has arboricity k if it can be covered with k edges, k spanning tree. Okay, a graph G has arboricity k if G has if E of G can be covered with at most k spanning trees. That's it. And but this is a concept which largely graph theorists don't use that much. It's largely used in distributed computing literature, right? Why again? Because if your graph has arboricity is small, you can like imagine the connectivity kind of questions that, because how does distributed computing works? Like it's like a round by round, you have to pass packages and this and that. So if there are small number of spanning trees, then you can route things cheaply in a small number of rounds. Okay, so this is, but there is another concept called degeneracy. Okay, what is another concept called? Degeneracy. So what is a graph? So we say a graph G is alpha D degenerate or D degenerate, or a graph G has degenerate a graph G has degeneracy alpha if for all subgraph H of G there exists a vertex of degree at most alpha. Okay, so what is a degeneracy? I say graph is alpha degenerate, D degenerate if you give me any subgraph of this, there is a vertex of small degree. In particular, the graph itself has a vertex of small degree, degree at most alpha. Okay, these two concepts are constant factor away from each other. Okay, so this is a good question to think. Okay, so how arboricity and degeneracy are related. Okay, so they are almost similar concept. Okay, okay. Now, okay, and so now let me make some comments on this part. So there we needed the fact that this happens. Now if I wanted an k edge disjoint spanning tree, why we went over partition? Let's try to think, like let's spend some time, like why it is important to have such kind of conditions. Okay, why not just like, oh, graph has too many edges is enough? Why a graph has too many edges is not enough? You get my question? If I say that okay, a graph has lots of edges, why it is not enough to find k edge disjoint spanning tree? Suppose if I said you n square edges, also some n square by 100 edges, can I guarantee that I will have lots of edge disjoint spanning tree? Yes, no? Why? Dead. Right? Graph is very dense, right? So we need to have a condition which essentially says, boss, you're dense. Like you have enough edges everywhere to support k edge disjoint spanning trees. Okay, or in other words, let me make it more nicer because it is not obvious, but like I could have replaced this condition with slightly different condition, and I could have said if and only if for all partition P1 to PL, for all partition P1 to PL where graph induced on Pi is connected, condition holds. there are at least k times L minus 1 crossing edges. I could have replaced with this condition that you don't have to go over all partitions, but even if you could support lots of edges over partitions where each part was connected in itself is good enough for our purpose. Why? Why? Imagine yourself that you have partitions, because here it talks about any partition. Now imagine that some part is disconnected, for example. So what is the meaning of this? This is what it is, no? You agree? So if this is what it is, now you break this into partition like this, for example. Did the number of edges increase, decrease? This partition has exactly the same set of crossing edges as before, because among them there are no edges. So in fact, if this partition, if this is true, then connectivity partition is true. Okay. So now what does this tells us? It tells us that, look, you look at your graph and you look at all graph H which can be obtained from following process: contract some connected sets, right? That should have enough edges to support k minus 1 edge-disjoint spanning tree. So these objects are called what is called contraction minors. So what did I tell you? I told you in the very beginning that given H, I can tell you how to get G. What is one way of edge? You just contract, you contract some edges. So when you look at the contraction and at the end, look at, so what did you do? Some contracted. Look at the vertices which are like new vertices because of contraction. Look at each vertex, they are like part, because why did all these vertices came together? Because they were connected among each other. So they automatically will imply, if you just unfold themselves, they will imply partitions of this nature, where each, right, and that has enough. These are like contraction minors. So these are the graphs which I can get from G by following set of sequence. What? You are only allowed to do edge, what do you call? You are only allowed to contract edges. Okay. And what does this statement tells us? This tells us, look, if every edge that you can get by edge deletion shouldn't have too many edges, right? So this is a property about subgraphs. This is a property about any edge that you can get as a contraction. Okay. So you understand now why we need that it should be everywhere dense. It in some sense everywhere dense, and it should be everywhere sparse, right? So if we want k edge-disjoint spanning to have, then we need to have a property that it is everywhere dense, in the sense like everywhere there are enough edges. And here it means, and what is the meaning of everywhere is given by that. Look at any I could have written this, if and only if every contraction minor has at least this many edges, and I'm done. So lots of literature will use that contraction minor, because that is the language which graph theories has taken in the modern era. Okay. So what are we going to prove? How are we going to prove this? So we are going to prove this amazingly theorem which tells us something very funky. Okay. Let me see, I will just write down the theorem. Okay, so what does it say? That it has best of both worlds in one statement. Okay. So what it says, G be a multigraph, okay, and K be element of natural number. Then there exists a partition P1 to PL of Vg such that following condition is held: 1, 2. Okay. First, for every I, graph induced on Pi, okay, graph induced on Pi has k edge disjoint spanning trees. Okay. So look at each piece They are very highly connected because they can support K. And if you look at G contracted P, meaning look at each P, contract to each of them, look at the graph by contracting. So what is the meaning of this contraction? Okay, the graph, you can think of this because you just find a spanning tree for each of P1, P2 spanning tree, okay, PL, okay, you contract this, or in more trivial way is like the graph which I made, no? P1, P2, PL, make a vertex and keep edges even if they are parallel edges. You have to allow parallel edges in the sense that otherwise how will I be able to, I want to keep all the crossing edges, right? So if there are 100 edges between P1 to P2, how many edges will I draw? 100 edges, that's it. And what does this tells us? The G contracted P edges of G minus G contracted P can be covered by at most K spanning trees. That's it, right? So it has both of both worlds. What does it tells us? For each I, G of Pi has K edge-disjoint spanning tree. Imagine that graph had K edge-disjoint spanning tree. What partition it will give me? Probably it will output me P equal to just one part. Alright, I mean it has best of both worlds. Now, do you see how you can prove both of these theorems given this theorem? You have to come up with this part, right? Okay. So I'll just give you just one, and I will let you think. Okay. So fix this partition. Okay, fix this partition. It's also partition, no? If I would have been applying this theorem, what can I say about the number of edges going across? Is at least, suppose this has L times K times L minus 1. Okay. Now, but these edges can be covered with how many edges? How many spanning trees? K. The edges going across. But each spanning tree has how many edges? L minus 1 edges only, no? So if they had, so you look at if you contract these guys and look at the edges which are going across, right? Can those spanning tree that covers all the edges here be what? Can they intersect? Because if they intersect, how many edges can they cover here? Look, now I know because of this theorem that if I contract and look at the crossing edges, right? Those crossing, look at these spanning trees as like W1, W2, WK. Each of them can cover how many edges? L minus 1 edges. Sorry, this is WK, so L minus 1 edges, L minus 1 edges. So how many edges they are covering? K into L minus 1, no? And you are telling me there are at least K into L minus 1 edges, so they better be edge disjoint. So now, inside there anyway edge disjoint, there are enough edge disjoint spanning tree. Outside also you have enough edge disjoint spanning tree. Can you combine them to get a spanning tree for G? That's one. Now if you try to prove this, you have to go inside and do something. That's it. Okay. So I leave it here, and on Friday, please, all I want you to like absorb the statement, try to prove these two theorems applying this statement. It's easy. Okay. And in the next class, we will prove this statement. Okay. So that's all.